This video is a review of electric force, field, and potential for AP Physics 2. I'd like to start out by talking a little bit about charge in general. We learned pretty early on that protons and electrons have a quality or a property called electric charge. And neutrons, however, the third particle that makes up atoms, are electrically neutral. And we talked about how the protons have a positive charge and electrons have a negative charge, and the magnitude of that charge we know, and it's on our equation sheet, is 1.6 times 10 to the negative 19 coulombs. So charge is measured in coulombs, and the charge of the proton and the electron is 1.6 times 10 to the negative 19. For the proton, that number should be positive, and for the electron, that number is negative, but in most cases, we're typically just working with the magnitude anyway. We also know that charge is quantized. If I take an electron off of something, then it loses some negative charge and becomes positive, and if I deposit electrons onto something, then it becomes negatively charged. But no matter how I remove charge or add charge to an object, the amount of charge on an object is either 0 or some multiple of the charge on the electron or the proton. So we could say that the charge of any object is some number n times the charge of the electron. So if an object is neutral, n is 0, and if an object has, in excess of 1,000 electrons, then n is 1,000. And so we should be able to express the charge of any object as some multiple of the charge of the electron or proton. Now I'd like to talk a little bit about electric force. We learned that electrically charged objects can exert forces on one another, and one of the unique things about the electric force is that it can be attractive or repulsive, whereas something like gravity can only be attractive. So if I have a plus and a minus charge, the force is attractive. 2 minus or 2 positive, the force is repulsive. And the equation that we use to describe those electric forces is Coulomb's law. Coulomb's law says that first, these forces are mutual electric forces exerted on either charge. So if I have a proton and an electron, the proton pulls on the electron with the same force that the electron pulls on the proton with. And that's demonstrated in Coulomb's law, right? In this equation box here, you can see that the product of the two charges helps determine what that electric force is. Which means that you can't have an electric force with only one charge. So not only do you need to have two charges, it points out the idea that charged objects cannot exert forces on other objects that aren't charged. You need two charges. And not only that, but Coulomb's law has an assumption, and that is, in order for you to apply Coulomb's law, the two charges need to be point charges. And a point charge is something that occupies a single point in space, or the size of the charge isn't important. And so that can happen in a couple of ways. Maybe I'm dealing with very small particles like a proton and an electron. That would satisfy Coulomb's law. Or if I'm dealing with two large spheres of charge, maybe two metal conducting spheres that have a physical size to them, then it's important that you know that when those charges get too close to each other, when those spheres get too close to one another, the separation between the centers of those two spheres is small compared to the size of those two spheres, and for that reason they don't really act like point charges anymore, and Coulomb's law cannot be applied. They'll start to polarize one another, and Coulomb's law just doesn't work. And so please remember that for Coulomb's law, the two charges need to be point charges. Now looking at Coulomb's law, the way that it's written on the equation sheet tells you a lot about how Coulomb's law should be used. It's written as the magnitude, or the absolute value of the electric force, is equal to Coulomb's constant, which is that letter K, which, as I've shown on the right, can be expressed as 1 divided by 4 pi divided by epsilon naught. Epsilon naught is a constant, but it's pretty rare that we ever have to write the expression out in that way. Typically, we just think of K as being Coulomb's constant, which is 9 times 10 to the 9. The product of the charges is in the numerator, Q1 times Q2, and please remember that we do not plug in the sign of the charge into Coulomb's law. We will use the magnitudes of the charges here to determine the magnitude of the force. Just like in my picture up above, I can always go up to a picture and determine which way the electric force is just based on my knowledge of what happens with the charges, whether it's plus and plus, minus minus, plus minus. And then lastly, the Coulomb force or the electrostatic force or the electric force is proportional to 1 over r squared. So there's a 1 over r squared dependence on the electric force. And so lastly, my bulleted list on the right, I've said Q1 and Q2 should be the charge magnitudes. Fe represents the magnitude of the electric force. The direction will always come from your intuition or your knowledge of the arrangement of the charges. And in order for Coulomb's law to be applied, the separation between the two charges r needs to be much greater than the physical size of the charged objects. A few more things on electric force. First, hopefully you remember that the equation for Coulomb's law for electric force has a very similar form to the equation for gravitation, Newton's universal law of gravitation. They both have a constant out in front. For the electric force, it's Coulomb's constant, and for the gravitational force, it's the universal gravitational constant. For the electric force, it's the product of the charges, and for the gravitational force, it's the product of two masses. And they both are proportional to 1 over r squared. These are referred to as inverse square laws. If you graph the force as a function of distance, you get this kind of a curve, where if I have a little sketch of a graph here, force versus distance would produce a graph that looks something like that. And we call those inverse square laws. And it's important that we know the differences between these two things. For two objects that are separated by a certain distance, and maybe they have some mass and they have some charge, in most cases, the electric force is going to be much, much more greater than the gravitational force, and that is primarily because of these constants that are out in front. The universal gravitational constant is, something times 10 to the minus 31, and Coulomb's constant is something times 10 to the 9. And so Coulomb's constant is like times 10 to the 40 greater than the gravitational constant. For that reason, it's really hard for the gravitational constant to be bigger than, it's really hard for the gravitational force to be bigger than the electric force. It's only when you have an object as big as the Earth or another planet or a sun that the gravitational force really becomes appreciable. In most other cases, the electric force is much stronger, and it's due to that Coulomb's constant being much greater than the constant in the gravitation equation. Also, I'd like to show that if I have a system of charges, so on the right I drew 3 different charges that are near one another, and maybe they're all the same distance apart. In a system of many charges, each one of those charges will exert a force on each of the other charges. And another point about Coulomb's law is that those forces are exerted along the line connecting each pair of the charges. And that's important, right? So if I'm looking at the plus 2q charge and the plus q charge, those charges are like charges, and so they will exert a force on one another that causes them to repel one another. And so those repulsive forces would be along this line connecting those two charges, pointing away from one another. And notice how I draw arrows of equal length even though they have different amounts of charge. And that's because the electric force exerted between those two charges will be equal and opposite on either one of those charges. And now if I look at the plus 2q charge and the minus q charge, those two charges are opposite, and so they will attract one another. And they will attract one another with a force that's equal in magnitude to the force from the previous two charges, because previously we had a plus 2q and a plus q. Now we have plus 2q and a minus q. The magnitudes of these pairs of charges are the same, but this time the force should be attractive. And then lastly, between the plus q and the minus q, those forces will be attractive as well along that line connecting those two charges. But since we're not dealing with the plus 2 charge anymore, the magnitude of these charges is slightly less than the pairs of charges in the previous cases, and so you should expect that the forces be a little bit smaller in that case, but still attractive. Now I'd like to talk a little bit about electric field. If you remember, when we started learning about electric field, we made a lot of comparisons to gravitational field. And so let's talk a little bit about that first. We know that Earth is surrounded by a gravitational field because of its mass. And observationally, we take a mass and we raise it up and we let it go and it falls back down towards the Earth. So this gravitational field is exerting a force on a mass that causes it to be pulled down. And so that gravitational field is defined as pointing in the direction that those masses feel a force toward Earth. You can also think of the gravitational field as being a force per unit mass. So the strength of the field is defined as the force that a charge would feel per unit mass, and that's also the expression that we use to generate equations for our weight, right? F equals mg. So on the surface of Earth, where g is equal to 9.8 meters per second squared, our weight, the force of gravity that we feel, would be equal to m times g. However, the gravitational force between any two objects, which is given by Newton's law of gravitation, g times m divided by r squared, if we set this equal to, or sorry, not set this equal to, but substitute this expression for the gravitational force into our equation for the field strength, we would find that the mass of the object on Earth's surface, that little mass, would cancel out, and we would get the following equation, right? We would get the fact that the gravitational field is equal to g, the universal gravitational constant, times the mass of the planet divided by the distance between those two objects. And for an object on the surface of Earth, that distance would be the radius of the Earth. Which means that if I plug in g, I plug in the mass of the Earth and the radius of the Earth into that equation in the blue square, I would get 9.8 meters per second squared, which is the strength of the gravitational field around Earth. And one of the interesting things that we find is that as r increases, g decreases. That's given by the equation, but it's also given by our intuition. As I get further away from Earth, the strength of the field surrounding it is getting weaker. Now looking over at electric field, we hopefully can observe a bunch of similarities. So charges are surrounded by an electric field due to their charge. So Earth was surrounded by a gravitational field due to its mass. Charges are surrounded by an electric field due to their charge. There were masses being pulled down to Earth for the gravitational field, and so we said that the force that they feel toward the Earth was going to be the direction of the gravitational field. And now for the electric field, we define the electric field to be pointing in a direction that a positive charge would feel a force. And so in my picture here, plus Q in red represents the source charge, the charge that is emanating the electric field, and plus Q in blue represents a test charge, a charge that I'm putting near the source charge in order to determine what's going on with the electric field. And we would find that that plus Q charge would be moving away from the other plus Q charge, and that's not only because they have like charges, but now with our understanding of electric field, the electric field points away from that source charge, and so the positive charge will also move away from that source charge. And that's because electric charges feel a force that is directed along the electric field lines. And so I made a similar couple of equations set up at the bottom here where I wrote Coulomb's law, which is K times Q divided by R squared, and I substituted that expression for the electric force into my equation for the field up above, and we again see that the field is equal to a constant times, instead of mass, here charge, but then still inversely proportional to the distance between the two objects squared. And similarly, as the two objects get further apart, the strength of the field goes down. Or I should say, as the test charge gets further and further away from the charge, we should expect that it would experience a smaller force because the electric field there is weaker. Along with our understanding of electric force and electric field is this idea that I can use a map of the electric field lines around some point charges to understand what's going on. So for example, if I put a positive test charge between these two charges on the left, I know it would be repelled by the top charge downward and attracted to the bottom charge downward. And so the net result of those two stimuli would be a larger force that points downward. And if I had an object on the left, I know that it would be repelled by a positive test charge, it would be repelled by the positive charge on the top, and attracted to the negatively charged object on the bottom. And so the net result of those two stimuli would be a larger force that points along the direction of the field lines. So we can always use the direction of the field lines to understand what direction the force points, but we should also start to get a knack for what the field will look like without having to draw in all of these force vectors, just because of our knowledge of the positive or negative nature of the charges. And so, for example, on the right hand side, if I put a positive test charge at this location, it would be repelled by the top charge, but also repelled by the bottom charge. And those forces, if we are in the middle between those two charges, would be equal and opposite, and that means that it wouldn't move. And for that reason, when we draw the electric field lines, none of the electric field lines can go there, because charges wouldn't feel a force at that location. And in fact, everywhere along this line between the two charged objects, we shouldn't expect there to be any electric field lines. The electric field lines should be asymptotic to that line, because no charge can feel a force along that line. And so while all of the electric field lines emanate away from a positively charged object, like for example here, due to this charge alone, it would feel a force away from that object. There's no crossing of the lines or no connected lines between two like charges. Lastly, I'd like to point out that if I just have a point charge, you notice that when we're very close to the charge, like for example here, the lines are very close to each other. But as I start to get further and further away from the charge, the field lines are getting further and further apart. And that's one piece of information that tells us something about the strength of the electric field. As the lines are getting further apart, the electric field is getting weaker. Electric force and electric field are both vectors, which means that they not only have a magnitude, but they have a direction. And so when I'm working with a couple of electric force vectors or a couple electric field vectors, I need to be careful about how I add these things together. So we know that electric force is given by Coulomb's law, but electric field is given by the following equation, right? Electric field is the force per unit charge. So you should not expect there to be a product of charges in the numerator. The only thing that's in the numerator is the charge of the thing that is emanating the electric field. And what this equation for electric field is really telling us is, for a certain distance away from a charge, what will be the strength of the electric field. So for a given charge Q, if I'm a distance r away from that charge, what will be the electric field strength at that position? The units work out such that electric field can be measured in newtons per coulomb, And maybe that's more easily demonstrated if you think of electric field as being a force per unit charge, where forces are measured in newtons and charges are measured in coulombs. And now if we look at this picture here where I have a plus Q charge and a minus Q charge, electric field points in the direction that a positive charge would feel a force. And so the electric field due to the charge on the left would be to the right, because a positive charge would be repelled by that charge on the left, and to the for the charge on the right, a positive charge would be attracted to that negatively charged object. So actually the electric fields due to both of these objects, both of these charges, would be to the right. And for that reason, if I wanted to find the total electric field at point P, which maybe is a distance r away from either one of those charges, then I would add the electric field vectors from both of them. If those electric field vectors pointed in opposite directions, I would have to subtract them, but here they point to the right for both, so I can add them. So kq over r squared plus kq over r squared gives me 2kq over r squared. And notice that the electric field is due to each single charge and has nothing to do with this little baby charge, this test charge that I'm placing in the vicinity of those things just to test for the electric force. And maybe an analogy that will help us understand that is that although Earth pulls on me, it exerts a gravitational force on me, my mass does not contribute to the gravitational field strength of Earth. If I got on a spaceship and flew away, the gravitational acceleration around Earth would stay the same. And so the strength of the electric field should not depend on the product of two charges. It should just depend on the product of the, or sorry, not the product, but the charge of the thing that's making the electric field. Please remember that we can also do this for force vectors, because electric forces are vectors as well. So if they point in opposite directions, we subtract them. If they point in the same directions, we add them up. And in particular, it's pretty important that if we're working with a couple of force vectors or electric field vectors that oppose one another, that at some point between two charged objects, there's going to be a place where the net force or the electric field will be equal to 0. And we saw that visually between the two positive charges on the previous slide, where none of the electric field lines made it to that line between the middle of those two charges. And so between two like charges, whether it's positive or negative, there should be a place where the electric field cancels to 0 and the electric force cancels to 0. The last big idea that I'd like to talk about is the idea of electric potential, which we also compared to gravitational potential, this idea of gravitational potential, which isn't something we talk about very much. We do talk about the strength of the gravitational field, lowercase letter g, 9.8 meters per second squared, and we do talk about the idea of gravitational potential energy, but we don't really talk about the in-between quantity, the idea of a gravitational potential, very much. A gravitational potential is basically a potential that tells me, independent of the mass, how much oomph there is at a location. So if I'm 1 meter off the ground, if the gravitational field were stronger there would be more of a pull downwards. Or in a given gravitational field, if I were just further up from the ground, there would be more oomph, more pull to the ground, or more energy associated with that position, if that makes any sense. And so the potential could be an important quantity because it's independent of the mass, but it still is relating to the location in a field and the strength of that field. And we'll see how that becomes important as we talk about electric potential. So charges moved away from a charge emanating an electric field have a potential energy UE. And an equation for that potential energy is written down below, which looks kind of similar to my equation for gravitational potential energy. Instead of mass, we have charge. Instead of gravitational field, we have electric field. And instead of h, a height, we have delta r, which represents a distance away from a charge or a distance between a couple of points. Importantly, For gravitational potential energy, we can define the gravitational potential energy to be zero at any location, so the particular amount of energy or potential at any one point isn't so important. But what is important is differences in gravitational potential or gravitational potential energy. And the same thing is true for electric potential energy. Differences in electric potential or electric potential energy are what's important. In the red box on the left, I have an equation for a change in electric potential energy being equal to a charge times a change in electric potential. And electric potential is a more well-defined quantity when we're talking about electricity. While E is the field strength and E times delta R represents the potential, we define the potential to be E times delta R, and we call that voltage sometimes. And so we've replaced E times delta R in this equation for electric potential energy with just delta V. And so if I have a positively charged object, as I've shown in the bottom there, emanating an electric field, which points away from a positively charged object, then as I move away from that object, I go through a displacement delta R, then the electric potential energy associated with that point will be changing. Perhaps one of the places where we were able to actually make some sense of electric potential was with a parallel plate capacitor, which was a device that, if I connect it to a battery, can store some charge on either one of the plates. And so let's say that each one of these charges can store an amount of charge on it equal to capital letter Q. And if each of those plates of the parallel plate capacitor, has an area of A, and the two plates are separated by a distance d, then we say that the capacitor has a capacitance of C. And the capacitance of the capacitor is related to the area and the distance between the plates as shown, but there's also a couple of other values in there. Epsilon naught is a constant, and K represents the dielectric constant. And a dielectric is just the material between the two plates of the parallel plate capacitor. And so sometimes we might have a material between there which helps build up the charge on the plates. And so if the dielectric constant goes up, it makes it easier to build charge because there's a higher capacitance. And if we don't put anything between the two plates, then while air is a pretty good electrical insulator, maybe it's possible for the charges, as they're building up, for the charge to spark across and break down the field between those two plates and allow the charge to flow. But that's not typically what we want to do for a capacitor, so sometimes we put a dielectric in between it to prevent the flow of charge. The potential difference between the two plates is defined as the charge on one of the plates, Q, divided by the capacitance of the capacitor, which for a typical parallel plate capacitor could always be figured out by using the equation that relates the area and the distance. And if I've connected a battery and there's been an opportunity for the charge to build up a little bit, then there's an amount of energy stored on these on the plates of these capacitors that's equal to 1/2 the charge on one of the plates times the potential difference. Or if you use the equation on the left to replace the charge, it could also be written as 1/2 the capacitance times the voltage squared. And so remember, there are several equations that might come into play when we're thinking about parallel plate capacitors. Not only the equation that determines the capacitance, but the equation that relates, the voltage between the plates, and the equation that tells us how much energy is stored on each capacitor. Here I wanted to just nail in the idea that if I have an electric field and I'm staring at 2 points A and B, that the electric potential at point A is greater than at point B. Right? If you kind of turn your head to the left, maybe it looks like those white lines are kind of pointing downward, similar to the way that gravitational field lines would point downward. And so In the same way that if you tilt your head to the left, that A would be higher up above the ground than point B would be, and we would associate that with a higher gravitational potential energy. Point A has a higher electric potential at that point because that point would be associated with a higher electric potential energy. So VA is greater than VB. The amount by which it's greater is whatever the potential is at point B plus E times the distance between those 2 points. And if I let go of a charge, a positive charge at point A, then it would move in the direction of the field lines to the right. And as it does that, the potential would be decreasing. So in general, we could say that potential decreases in the direction of an electric field. A pretty important point, something I think you should remember. But also, if that's the direction that a positive charge would feel a force, then if I wanted to hold the object there, or if I wanted to move it to the left, opposite the direction of the electric field, for a positive charge, I would have to do work. And the amount of work that I would have to do in moving a positive charge from point B to point A, for example, would be equal to the magnitude of the charge times the potential difference through which I move. Right? So W equals Q times delta V. And lastly, the equation which relates the voltage, position, and electric field together illustrates that electric field can not only be measured in newtons per coulomb, but it could also be measured in volts per meter. So make sure you're familiar with both of those units for electric field. The last point that I'd like to remind you of is the idea of equipotential lines. So we've talked about electric field and electric field lines. Now we've talked about electric potential. And an equipotential line is a line where everywhere along that line the potential would be the same, right? Equal potential. Sometimes we refer to them as isolines of equal potential. These lines are perpendicular to the electric field lines, and sometimes the electric field lines can be useful for finding lines of equal potential, or lines of equipotential can be used to generate a map of the electric field. And so these yellow lines are certainly not the electric field between these two oppositely charged objects. Electric field lines are supposed to point in the direction that a positive charge would feel a force, and these lines don't demonstrate that. These lines are equipotential lines, and if I were to start at one of these charges and move perpendicular to these yellow lines, it should generate the electric field between these two charges. And so if I start on the left and I move perpendicular to these lines, you can kind of see that maybe I am going to generate lines that are the electric field lines. For example, if I run straight in between these two, perpendicular to all these lines is a line that runs straight from one charge to the other. And if I go just a little bit out, while I'm doing this very quickly, right, you could roughly guess that if this was done a little bit more carefully, that quite clearly we could get a pattern of electric field lines that looks quite similar to what we saw on the previous slides. And so please remember that equipotential lines can be used to generate the electric field, and that they are lines where the potential everywhere along them is the same, and that they're perpendicular to the electric field.